Okay, so there's three main factors that actually affect the wind the most. The first is the pressure gradient force, the second is the Coriolis force, and the last one is friction. So pressure gradient force, this goes back to the isobars. Okay, so again, isobars are lines that connect in places of equal pressure, right? If the isobars are close together, like they are down here, you get strong winds. The winds are really gusty, they're really fast. This is also known as a steep pressure gradient. Okay? However, if they're more widely spaced, like here, it's a weak pressure gradient, which means weak winds. So this is how it works. Right before sunrise, everything is a nice equilibrium, right? We have, okay, it's showing 10, 12 instead of 10, 13, but whatever. You're basically your sea level pressure straight across, ocean to land. And you go up a little bit, remember it decreases as you go up, so we got 1008, ocean, land, 1004, ocean, land. That, you get the idea, right? But then what happens is you start to heat up the land. Remember, the sun rises and the sun will heat the land faster than the ocean. We talked about that. And so it starts to heat up the land and it starts to spread out that pressure. You start to get a weak pressure gradient. Well, here your numbers, they spread out, so you have 1,000 where you used to have 996. So that makes the land have a higher pressure. Well, everything wants to go from high pressure to low pressure. So it goes over to the ocean. See, from high to low pressure. Well, now everything's starting to converge here. There's too much air, so it starts to drop down to the higher pressure. That means that this lower pressure is starting to spread out. That means this is a high pressure. Everything wants to go from high to low. So it goes over into the land and it starts to diverge away. So you get it diverging into a high. And then back to your low, and you get your circle here. Now the pressure gradient force is the most important force out of the three of them. It is the one that affects the wind the most. The Coriolis force doesn't affect the strength of the wind. What it does is it affects the direction of the wind. So in the Northern Hemisphere, everything deviates to the right. In the Southern, everything goes to the left. This is why hurricanes spin. And they spin clockwise. Sorry, counterclockwise. They spin counterclockwise in the Northern Hemisphere. It all has to do with the Coriolis effect. This is the picture I like. So, where you are on the planet determines how strong this Coriolis effect is. If you're at the equator, it actually doesn't affect you. And you can see these arrows going straight across, not affecting you. However, if you're up at like 20 degrees or at 40 degrees or 60 degrees, you can see how much deviation from the straight there actually is, right? A little bit more and even further. That's because of the spinning of the Earth. This is a great video that explains it.
If you've ever watched the news during a hurricane or wintertime nor'easter, you've probably noticed that big storms spin over time as they travel. In the Northern Hemisphere, they spin counterclockwise. But if you were watching a storm in the Southern Hemisphere, you'd see it spinning clockwise. Why do storms spin in different directions depending on their location? And why do they spin in the first place? A storm's rotation is due to something called the Coriolis effect, which is a phenomenon that causes fluids like water and air to curve as they travel across or above Earth's surface. Here's the basic idea. Earth is constantly spinning around its axis from west to east. But because Earth is a sphere and wider in the middle, points on the equator are actually spinning faster around the axis than points near the poles. So imagine you were standing in Texas and had a magic paper airplane that could travel hundreds of miles. If you threw your airplane directly northward, you might think it would land straight north, maybe somewhere in Nebraska. But Texas is actually spinning around Earth's axis faster than Nebraska is, because it's closer to the equator. That means that the paper airplane is spinning faster as well, and when you throw it, that spinning momentum is conserved. So if you threw your paper airplane in a straight line toward the north, it would land somewhere to the right of Nebraska, maybe in Delaware. So from your point of view in Texas, the plane would have taken a curved path to the right. The opposite would happen in the Southern Hemisphere. An object traveling from the equator to the south would get deflected to the left. So what does this have to do with hurricane spinning? Well, at the center of every hurricane is an area of very low pressure. As a result, the high-pressure air surrounding the center or eye of a storm is constantly rushing toward the low-pressure void in the middle. But because of the Coriolis effect, the air rushing toward the center is deflected off course. In the Northern Hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right. The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the Southern Hemisphere, where the Coriolis effect pulls air to the left, the opposite happens. Storms spin around the eye in a clockwise manner.
Alright, so the last thing that affects wind is friction. And friction affects the wind more when it's close to the ground. As you get higher up in the altitude, it's not going to affect the wind as much because, well, there's nothing to have friction against other than different air. When it's close to the ground, it's got friction going over the mountains, going over through the valleys, going over the canals, what have you, buildings, etc. So if you have friction, you actually drop your wind speed. And if you don't have friction, you can go faster. It's kind of like these water slides, right? This one doesn't have a bump. This one doesn't really have friction. So, bing, done, right? Whee, done. This person has a bump here. Consider that friction, right? It goes wee, 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 right? Then you slow down over that bump. And it causes you to slow down overall. So increase friction, drop in wind speed.